problem, we have a situation where the distribution of this random variable x is binomial, right? So this is how you write these kinds of things out. And n is equal to 10 because you're buying 10 of these broccoli plants. And the probability that any one of them would not produce broccoli was 0.05. Okay? So we can say n comma p. That's how we denote this. So it's 10 comma 0.05. All right? 8.8 from your Yates textbook. What version is this? Third edition. Okay. It says find the probability that you will lose at most one of the broccoli plants. So we're really saying find the probability that x is at most 1. That's what they're asking for. Okay? So if we think about our random variable, there's two cases that work. What would make us happy? Well, if none of them died, that would satisfy this condition, right? If all of them produced broccoli. Okay? Or if one of them didn't make it and did not produce broccoli, we would still be happy. Okay? But anything more than that doesn't fit into this category. So these are the two probabilities we need to find. Okay. We have a formula for the probability that x equals exactly k. And it's this. It's n choose k probability of what we're worried about or what we want to happen to the k power, and then 1 minus and the probability of what we don't want to happen to the n minus k power. So in our case, for that first problem, n is 10. We're buying 10 plants. We don't want any of them to die. The probability that one of them dies is 0.05. We don't want that to happen at all. And the probability that any one of them lives is 0.95, and we want that to happen 10 times. That's the first probability that you need to worry about. Okay? Right? Now, this you could actually calculate in the calculator using something called the binomial PDF. And it always has n comma p comma k as the parameters that you enter, right? So n is 10, probability is 0.05, and we don't want any of them to die, okay? So if you type this in the calculator, it would give you the value of this expression we have here. So let's do that. So go to the calculator. You find that in distributions. You do second vars to get the distributions. Go up, and you'll see the binomial PDF. We hit enter. It's 10, comma, 0.05, comma, 0. And you hit enter. We get that probability. So 0.5987 is equal to 0.5987. That's one of the cases we're worried about. We're also worried about the case when x is equal to 1. We have to worry about that case. Well, so this one's going to be 10, choose 1. Now this time we're saying, okay, if one of the plants might die, and then the other 9 plants live and produce broccoli. Okay? So let's do that in the calculator. It's actually the same thing. I'm going to do second enter, and I'm just going to change that 0 at the end to a 1. Enter. And we get 0.3151. Okay? So this equals 0.3151. Now all we want to do is add those two probabilities together. If we do that, we get a total of, so this gives us 0.914. Now, it's important to note that you could do this very quickly. If it was a multiple choice question, we didn't have to show any work. Here's something you could do. Probability that x is less than or equal to 1, okay, can be done in the calculator, actually, as a binomial CDF. We discussed that, but the binomial CDF gives you the probability. This gives you the probability that x is less than or equal to k. So you would just do 10, comma 0.05, comma 1, and it will sum those two cases, the case of 0 and the case of 1 for you. So watch this. Second distributions, and we go up, and then we find the binomial CDF. Those of you who are wondering, CDF stands for cumulative density function. All right, so we do 10, comma 0.05, comma 1, close parenthesis, enter, and there's that number you get when you add the two probabilities together. So let's consider a different problem. So let's consider a problem that is binomial. Okay, we got another random variable x, actually. that's binomial with the parameters n and p. Right? So in this case, n is 20 and p is 0.8. The problem, this is problem 8.10 from Yates' book. Here's what it says, right? The university claims that 80% of its players graduate. An investigation examines the fate of all 20 players who entered the program over a period of several years that ended a few years ago. Of these players, 11 graduated, and the remaining 9 are no longer in school, right? So remember, the university claimed 80% of their players graduate, but now, in this particular example, only 11 graduated out of the 20. All right, so the first question we're going to ask is, what's the probability that x equals 11 if x is the random variable, which is the number of players who graduate? So the question is, how likely is this to occur, right? All right, so let's finish this problem off. So we would have, first off, this distribution has n20 probability of graduating of 0.8. Now, keep in mind, this probability of graduating of 0.8 is a claim the university is making. So this is going to be a fun little result to do. We're saying, what's the probability exactly 11 out of 20 graduated if their claim is true? Well, it would be 20C11, 0.8 to the 11th times 0.2 to the 0.9. If we do that, that's really, I'll abbreviate this a little bit, it's a binomial PDF of 20, 0.8, 11. So we're finding the probability exactly 11 out of 20 graduate. So let's go do that. The second distributions, binomial PDF. There it is. Oh, I pressed the wrong button here. Clear. Second distributions. Easy to do that. And there we go. So binomial PDF, 20, because there's 20 players. Probably any one particular player graduates is 0.8 according to the university, comma, and 11. All right, we hit enter, and we get a very small probability. The probability is about 0.007. So what this is telling us, it's very unlikely that exactly 11 out of 20 students graduate if, in fact, the true graduation rate is 80%. This might lead us to not believe the university's claim because we've observed something that really shouldn't happen. They're saying, hey, look, 80% of our students graduate, and then 11 out of 20 graduate, and you say, hey, wait a minute, the probability of that occurring is only less than 1%. So we observe something that's very rare. That leads me to not believe the claim. Okay, let's find out the next part. Let's find what probability that all 20 graduate. What's the probability that x equals 20? Well, that's 20C20, 0.8 to the 20, 0.2 to the 0. Okay, so let's see what that turns out to be. I think I'll just do second distributions here and change that 11 to a 20. Hit enter, and I get a 0.0115. 0.0115. So that's pretty unlikely, too, and I'm not surprised by that. Okay, and then the last question is, what's the probability that not all 20 of them graduate? Okay, well, probability that not all 20 graduate. So it's hard to write that. Or we can actually write it this way. We can say probability that all 20 graduate, say probability that x doesn't equal 20. Well, that would equal 1 minus the probability that x equals 20, or 1 minus 0.0115. And this question was sort of asked in that way to remind us that sometimes when you go to find a probability, it's easier to find the complementary event and then subtract from 1. So I think we get 0.9885 here. So it's very unlikely that all 20 graduate. We would expect that. You could have done this problem. That's probably the best way to do it. The other way to do it is this. You can also think of this case as saying this is really the probability that x equals 0, that none of them graduate, or one of them graduates, or 2 of them graduates, or all the way up to 19 of them graduate. That's sort of a fun thing. I'm writing it that way because you can clearly see, in this case, you could write this as a CDF. This is really just a binomial CDF of 20, comma, 0.8, comma, 19. And we put that in the calculator, we'll get the same answer. Let's verify that. Okay, the second distributions here. Let's go up. A binomial CDF, 20, comma, 0.8, comma, 19. And you get the same number. Now, it's a little bit rounded there, but you can see it's 0.99, 0.9885. Okay, thanks for watching.